Hello everyone, this is mechanics of materials, and in this video we start to talk about the distributed loading. Okay, I think this a new term. Probably the new term to you or for most of you. Okay, and okay, at the beginning of this class, we have just say that what is the mechanics of material? The mechanics of material, the aim of this course is trying to let you understand the relationship between the external loads and the distribution of internal forces, and also find the deformation. Okay, we have a material. Okay, we may apply a lot of external load on the material. Okay, and then we want to know the distribution of internal forces and the external load. Okay, and external load, there is a very special external load called distributed loading. Okay, although the terminology seems to be rarely seen in your daily life, but it happens a lot in your daily life. Okay, the distributed loading looks like this. Okay, suppose we will have a beam here, and we have placed a lot of bricks on the beam, and you will see that the number of bricks is not the same along the whole beam. Okay, the right hand side we have we have more bricks on the right hand side, and at the middle we only have just one bricks. Okay, so this called distributed loaded. Okay, distributed loaded. Okay, loading along a single axis. It's called distributed load along the axis. Okay, actually this happen a lot in mall, especially when you go to the Costco. Okay, Costco, because there is a bin over there. There's a bin here, and you have a lot of stuff placed on this beam, and you will see the stuff on this beam is not uniform because some is high, some is low, some is low, some is high. Okay, so the load on this beam is not uniform. It has some distribution. Okay, it has some distribution. So this is called distributed loading. Okay. Okay, of course, if you have constant loading on the beam, it's also one kind. It's also belong to a distributed load. Okay, but most of the time when we talk about distributed load, okay, that means the load is not uniform. It's not uniform. Okay, in general case, it's not uniform. Okay, yeah, the uniform loading is a special case of distributed loading. Okay, and I'm not sure in Taiwan, but if you go to Home Depot, okay, Home Depot, yeah, Home Depot also see a lot of stuff like this. Okay, there's a bin over here, and the bin, a lot of stuff on this bin is not uniform. It's not uniform. Okay, so it's a distribute loading. Okay, and this also happen in your plane. Okay, we know you have plane, you have the wings, and we know if you want to lift up a plane, you have apply a lift force on the wing, and then your plane will take off. Yeah, and the lift force on the wing is not uniform. Okay, it has a distribution. It has a distribution. For example, for here, the wing at the tail of the wing, at the end of the wing, it's the lift force is smaller, but when you go to the center of the plane, and the lift force is stronger. Okay, so there's a distribution load on this wing. Okay, that's a distributed loading. Okay, okay, so that's the distributed loading. Okay, that's the concept. Okay, and this distributed loading, when we do this happens a lot. Okay, so we have to and then for when we come to distributed loading, we have to use a systematic way to simplify the system for the further calculation. Okay, so in this section, I will show you how to make a reduction of simple distribution, make reduction of a simple distributed loading. And we just use what we just learned, simplification of system. Okay, right now I have a distributed loading system, and I want to make a simplification, make it become just one single resultant force, and locate where and also want to know where is the resultant force acting. So we have two objects, just like we did on further simplification problem. First of all, when we have a distributed loading, first of all, we want to know, okay, we want to find what our goal. Okay, first of all, find the resultant force. Okay, and then determine the position of the resultant force. In this picture, it's called, I think here it's called X bar. X bar. Okay, X bar. That's our goal. Well, suppose I have distributed load system. I want to make a simplification of system for further analysis. Okay, so the simplification, we have to find out what the final resultant force and where is the resulting force acting. Okay, so find the FR and X bar. Okay, so, and next I have to show you how to do the simplification. Okay, I think, okay, so let's start with it. Okay, for the distributed load, we have to introduce a new terminology called WX. Okay, okay, what's a WX? WX. Okay, WX is a, okay, when we have a distributed loading, we have a WX. A WX is a, what can, load distribution function. Load distribution function. Distribution function. And WX is not a force. Be careful. WX is not a force. Its unit is it's like for a simple for a 1D problem. Okay, it's a, oh, sorry. Oh, it's sorry, my pen has some issue here. Okay, its unit it's force per unit length. Okay, so the WX load distribution function is not a force. It's a force per unit length. Okay, for a one-dimensional distributed loading, it's a force per unit length. Okay, so it's not a force. Okay, so okay, we have to make sure this, because this W distribution function is not equal to force. Okay. And when we write the WX in mathematics, because the load distribution function, so actually, if you write using mathematics to express the WX, it's delta F, its distribution. So your tiny area, so it's delta F over delta X, and it's just equal to dF over dx. Okay, so derivative of force with respect to x. Okay, if you write Wx in mathematics, that's its definition. Okay, so so next thing. Okay, so first of all, when you do a simplification, first of all, find a resulting force. Okay, and for a distributing loaded system, like I said, distributed loaded system, we have lots of force pointing downward. We have a lot of force pointing downward here, just like this graph. Lots of force pointing downward. And so we don't, for this derivation, we don't use the convention. Okay, because in convention, point down is negative, point up is positive. But for this derivation, I just say, okay, I make another definition. I say point down is positive. Point down is positive. That will make the whole derivation looks more nice. Okay, because if you use the convention point down is negative, you will have write a lot of negative sign in the derivation. That will looks very awkward. So in here the analysis, we just use a point down is positive. So you will see this symbol here, that's positive, and point down, that means point down is positive. Okay, and the resultant force, that's what I'm trying to calculate, resultant force. Okay, and the resultant force, because when we have distributed load, there are lots of tiny force point downward. Okay, so actually at the very beginning, it's the summation of delta F. Okay, because there are many tiny force point downward. there are a lot of tiny force pointing downward, right? So it's summation of delta F. But if delta F is very, very small, okay, this symbol will become, this summation is equal to the integration, okay? So that's the first step, okay? It's just adding lots of small force, adding lots of tiny forces, okay? Adding lots of tiny forces here, okay? And then we make a trick. Okay, like I said, I can write the df become df over dx and times dx. Okay, this is a trick. Okay, this is a trick. Okay, we can write df become df over dx times dx. Okay, that's a trick used a lot in calculus, right? Okay, and then we just say, okay, df over dx is just df over dx is just your load distribution function. Load distribution function. So this will become wx. So the integration will become, the resultant force will become the integration of wx w of x times dx. And what is this mean? Okay, so let's cut this slice area here. Let's cut this slice. Let's zoom in this slice. Okay, here I think let's cut a slice here. Okay, here we have x here, and then here we have this point is cut a slice here, and this x plus dx, and the height here is wx. Okay. Okay, so what is wx times dx? Okay, actually the dx is the width. Okay, let me erase this. Okay, actually dx is here. Can you see that? This is dx. Yeah, did you figure this out? Do you figure this out? Because this x, yeah, and there's one more small step further, x plus delta x dx. So this width is dx, and the height here is wx. So here is the wx times dx. Could you understand this? So actually the grade area is just equal to w of x times dx. Okay, so the wx times dx is the area of this small slice. Area of this small slice. Area of this tiny slice. Tiny slice. Okay, so the area of tiny slice, I call it dA. I call it dA, and then I summation lots of dA along this x direction. I summation lots of area of this slice and add them together from the left hand side to the right hand side. Here, suppose here is 0, and let me complete the graph. If here is L, okay, and I add this small slice, add the area of this small slice from the left hand side 0 to the left hand side 0 to the right hand side L, and add this small area together. It will become the area under the curve, area under the distribution load curve. So that's A means area under the curve of Wx. Okay, so the conclusion is here. Suppose we have the distributed load on the beam, okay, and we want to do the simplification of the system. So the simplification of the system, we want to find a resultant force. How to find a resultant force? You just find the area under the curve of a distribution function of forces. Okay, find the area under the curve of W of x. Okay, that's your resultant force. Okay, that's the conclusion. Okay, so let's write a small conclusion here. Okay, first of all, what our goal is, what is FR? What is FR? Okay, area under the curve. I shouldn't use this color. Is there a better color? Hmm. Okay, what is this FR? Okay, area under the curve of WX. Okay, let's do FR. Okay, that's the first thing we got. Okay, the second thing is how to we want to know where is this resulting force acting at. Okay, so simply speaking, where is the resulting force or the position of resulting force? Okay, the position of resulting force in this 1D system. Okay, so that's another goal. Okay, so let me erase here. Okay, and how to find the position of the resultant force. In the previous example, when we did the simplification problem, when we try to determine the position of resulting force, we use the moment balance, right? Use the moment balance. Okay, before simplification, after simplification, your resultant force must be the same. Also, your resultant moment must also be the same. Okay, and we can use the moment balance to determine the position of the resultant force. And here, for distributed loading, we use the same concept. Okay, actually, we really use the same concept. Okay, so and right now I have to erase these things. Okay, because we have to go to the next slide. So I have to erase this out. So if you want to take a note, just please rewind. Okay, because we have to go to the next slide. Okay. Okay, use the same concept. Use the moment balance. Moment balance. Or the before simplification, after simplification, the moment must be the same. Okay, okay. So next slide. Okay. Okay, location of resulting force. Okay. Okay, we use the moment balance. Okay. Okay, this is after this is before simplification. Simplification. Okay, this is after simplification. Simplification. So after simplification, we only have one resultant force, right? We only have one resultant force, Fr. And the position we don't know, we call it X bar. Okay, so this is the moment caused by the resultant force. Okay, after simplification. So it's Fr times the X bar. Okay. And this term here is the moment by the distributed loaded. Okay. Like I previously said, there is a tiny force acting on the beam, point downwards. Okay, so the moment, okay, the moment caused by the distributed load, we have tiny force. We have tiny force. Okay, and tiny force, and you're going to calculate the moment. You need the full magnitude of the force and times the lever arm. Yeah, the lever, suppose we have tiny force here, the lever arm just this x. Suppose we are talking about the position x with respect to the origin O. Okay, here's a position x here, here's a position x, and we have tiny force at this x point, and the df and point downwards. Okay, and because it's a point downwards, so the lever arm is just the x. Okay. Okay, just a tiny moment. Okay, so I call it dm. Okay, and then I want to act this all tiny moment together, so I use integration on both sides. Okay, so we just make it become df times dx, but this all look awkward, so it's equal to x df. Okay, and the summation of all tiny moments, all tiny moment together is all equal to the total moment. Okay, so here is that's the meaning of this xdf. Just uh the the resultant moment caused by tiny force. Okay, resultant moment by by tiny moment. Okay, the resultant moment is let's add all the tiny moment together. Okay, by adding sorry is by adding tiny moment. Oh, there are lots of tiny moment here, tiny moment, and add them together. It will become a total moment of the system. Okay, so this is a moment by, so that's why it's equal. Before simplification, after simplification, there must be the same. Okay, that's why this is the equation here. Okay, it's very important. Okay, it's just what we learned, simplification of the force and couple system. Okay, and then we also make a trick. Okay, because like I said, I can make a trick. I make a trick df. Can you write df over dx times dx? Okay, let's calculate trick. So it's just equal to wx times dx. So here, so this will become x times w of x times dx integration. And we already know that, okay, the w of x times dx is just a tiny area, right? We just in previous slide, we just explain this. W of x times dx is tiny area. Is a tiny area. Okay, so it is. So the resultant force times x bar equal to x dA, and doing the integration. And in previous video, we already know the conclusion is the resultant force is the area under the curve of W of x. So, okay, so the resultant force actually is A. Okay, it's area under the W of x curve. Okay, so here we have this equation will become like this: A times x bar equal to x dA. And then what is x bar? X bar we are going to after is A is the denominator, and then A is in denominator, and numerator is x dA integration. Okay, so let's the final expression of the position of resultant force. Actually, this definition, the right hand side, is just equal to the definition of the centroid. Okay, so the conclusion here is, where is x bar? The conclusion here, what is x bar? Okay, centroid of the area under W of x curve. Okay, so we have two final conclusion. Okay, for distributed load. Okay, first of all, what is the resultant force of the redistributed load? Okay, area under the W of x curve. W of x is a load distribution function. And where is the resultant force? Okay, it's the centroid of the area under the W of x curve. Okay, so you may find the conclusions all relating to the area under this curve. Okay, yeah, you will see that the conclusion is all related to the area. It all relate to the area of this under this curve. Yeah, the resultant force is the area under this curve, and the position of resulting force is the centroid of the area under this curve. Okay, it's all about this. It's all about this area. Yes, that's true. It's all about this area. Okay. Okay, so this is a concept for the simplification of the distributed loaded. And I think in next video, because I will introduce in the next video, I will introduce what is called centroid. Okay, I will do some review on centroid. And the centroid, I think you might all learn this before, because I think in maybe high school physics or freshman physics, you will all learn about the center of mass, right? Actually, in typical situation, centroid is just equal to your center of the position of center of mass. Okay, so they are actually very similar. Center of mass is just very similar to the centroid. Okay, and centroid in Chinese called 行星 or 形状的中心, 行星. Okay, so we'll talk about the centroid in next video. Okay, and after talk about centering and when then we go back to the example of the distributed loading problems. Okay, so I just stop a video here. Okay, okay, hope you can understand this topic. Okay, see you in the next video. Bye bye.